If I don't know your name, you should try to make sure I know your name, because if you talk to me all the time in class, I probably know your name. Otherwise, I probably don't. And I want to make sure that everybody gets credit for being here and for participating. So yeah, it's on you guys at this point. Yeah, Mia.
We're talking about, like, in the cloud, hydrogen gets charged, right? And then that's when it starts to stick together and it starts to, that's what they theorize, kind of starts that process of a new star.
Yeah, these little trihydrogen, I think it's trihydronium clusters. This is kind of this is a very new hypothesis. The problem, like, to back it up a little bit, the trick is that you need to, and this story has evolved a lot, even in the 3 years I've been teaching this class. It's kind of wild, actually. So it used to be that the story of solar system formation and star formation was like this gravitational collapse of a cloud. And so I would talk to astronomers, all the time on my podcast and talk to them about this process. And it's, always, it was often said, like, if you add up all the atoms in these enormous, 3 to 10 light year wide clouds, you have a lot of mass available. The problem is people started looking at these and they realized that most of these clouds actually aren't collapsing gravitationally. Like, a very, very small percentage of them are. And so you have to look at new ways to nucleate these sites. And some of that comes from the pressure of pre-existing stars, right? Of course, that gets you into trouble later when we get cosmologically speaking. If there's a start to the universe, then at some point you got to make stars without other stars being around. But one thing that's really opened up is this condensation chemistry stuff that's really beginning to appear that I find particularly appealing myself, because once you get little molecules condensing, especially charged molecules, they have the ability to stick together, which is quite interesting. So yeah, the hydrogen cation is quite exciting. Could be a point of making little clusters of this gas to something approximating a droplet. Of course, then you end up with a liquid model for the sun, which is very different than the popular one for the last century, if you haven't figured it out already. What else, guys? Yeah.
I'm Courtney.
What's that?
Courtney.
Courtney, sorry.
I just
Gotcha.
thought that it was really interesting kind of going along with the stars being born and how we've never actually seen a star being born because it's in the cloud. Something I didn't know. I kind of thought that we had figured it out, based on being able to see it happen. So it's something really interesting.
Yeah, it's really difficult. That's the one part of the puzzle that's hard to solve. We've never seen a star forming per se. We've seen things that we think might be where stars are forming, best candidates, but that actual process to see it happen, even if we go with really liberal estimates of how fast this moment can take for something to condense like this, it still takes thousands of years, if not millions of years. And so trying to see something like that in real time is going to be eluding us eternally. So, yeah. What else, guys? Who else has got thoughts? Yeah, Jasmine.
So, talking about astrochemistry, I don't know if we talked about it, but how are they able to receive the chemical bonds and elements for the certain stars that they're observing? So how can they look at the star and be like, okay, there's hydrogen, helium, all this stuff? Is it based on pure coincidence, or?
Well, those are a couple different questions. So, how do you know elemental abundances is one question, and then, well, I guess they're kind of related. So it all comes down to light, right? So you get different kinds of light from charged molecules versus uncharged molecules. Actually, uncharged molecules are really hard to see the light from. That's why I spent all that time talking about the spin flip process for the neutral hydrogen. Otherwise, most molecules that are charged start to give off really nice signatures because they're essentially, they have transitions available to them. Their shells are doing really interesting, they're exploring new spaces, which results in light signals to their neighbors. In terms of the elemental abundances, it's kind of similar. You get fingerprints from different elements, the light signatures from them. But you can also measure the density, right? So that comes from a lot of gravitational interactions and so forth, how things are reacting, how much light's getting screened out by them when it comes to neutral atoms. So these clouds often appear, very dark, or they'll screen out blue light, sort of like our atmosphere does at sunset. So there's all these indirect ways of looking for what's out there. But it's tricky. It is very tricky. And the estimates are always being updated and refined. So yeah, this is one of the more nebulous processes we're talking about. No pun intended. What else, guys? Yeah, Mercedes, yeah?
So like going back to like not knowing how the stars are forming, like what is like an estimate to where we're totally wrong about how they are forming? Since we can't see it.
Let me make sure I understand your question. Like, where have people been wrong about this in the past?
Well, yeah, and like how are we so sure that it's happening?
Yeah, well, we're not, but we do see a lot of stars, and, in some sense, the entire story of this course is a story for the stars, right? And little pieces of that story inevitably change over the years as we learn more and more about them. But presumably, stars have to come from somewhere, right? We do see occasionally, although very infrequently, we see stars die. So if the stars are, I don't know a better word than dying, it's very morbid, but they stop shining. And a lot of them undergo these, not a lot of them, but occasionally we'll see these explosions. So stars have to be coming from somewhere too, presumably, right? And so people try to both theorize how that could happen and then look for signs of essentially, where there's evidence of those processes happening. So these clouds that we talked about, these polar jet streamers that are leading back to a point inside of a cloud are kind of the best guess. It's very, very tricky. I would say that, the story of how to make these things, in some sense, is easier and there's less controversy surrounding how these things are made than how they die, which we're going to get into next week. Because some really weird pieces of data about these stars disappearing, and we see, like I said, very few of them do we see explode. Right? There's very, very few supernova. I believe the last one that was observed in our galaxy was in the time of Galileo. So, but on the other hand, there's been some really interesting evidence about stars kind of just going missing from the night sky. So there's kind of two stories to be told there. In terms of making them, I mean, a lot of the real controversy lies in the story we're going to get into today, which is how to make a planet. And so we talked a bunch about that last semester. I think David's the only person who's here for that. So David can just teach the class for us, hopefully. So the how to make a planet it has some obvious places where we can update our understanding. The star stuff, it seems to be on the right track as far as I can tell. There's a lot of new ideas. There's people studying chemistry in a way that doesn't just kick the can down the road to gravitational collapse. I'll get to you in one second in the back. The thing with the gravitational thing, I used to beat on it a lot in previous years. It doesn't seem to be as big a piece of the puzzle already, which is cool. This is exactly how you want science to proceed. Problems one year get sorted out and people kind of move forward with them in a more productive way. The gravitational collapse stuff was always a little disturbing to me because it's based on the way that these clouds are treated in this collapse scenario is based on ideal gas laws. And if you guys remember high school chemistry at all, the ideal gas laws always require a container in order to generate this gas pressure, essentially. And if there's no container, then it's very hard to justify how you have any kind of pressure necessary in these clouds to do the work necessary to even nucleate these reactions, let alone collapse them. And then we talked about issues with the second law of thermodynamics. And not to bore you guys to death, but it's very difficult to explain why, if you popped a balloon in space, why it would ever come back together. Presumably, thermodynamics would say that the gas molecules would just kind of drift apart indefinitely. So Yeah, I think there's a lot more interesting work going on with the condensation chemistry, with the electrochemistry processes that seem to be capable of nucleating local density in a way that, once you get something built, once you get a pretty big droplet going, you can actually start to see appreciable effects of gravity. It's right around the size of a Jupiter, actually. So that's kind of interesting. In the back, remind me your name. Antonio.
I was just messing with my hair, but
Oh, all right.
I'll ask a question.
Yeah, do it.
I'm kind of confused on, like, you talked about the collapse of the star, and to my understanding, it's because of the, like, gravity is stronger in the middle of the form. What happens if it never gets, like, if gravity's never stronger than the middle? Does it just, like, go away?
Yeah, I mean, all this hydrogen is just piling up because it's getting spewed out of every star, just like our solar wind. Our star is doing the same thing. It's what's responsible for all, you hear about space weather, and you hear about these coronal mass ejections and stuff. I mean, these are just chunks of hydrogen just ripping off the sun, and every star is doing that in every direction. So there's just a big foam of this stuff, right? That's what these clouds are essentially made out of. I mean, so yeah, you have to get a site that's locally dense. And a big part of that puzzle, too, is that it gets really cold inside of these clouds. Light can't reach them, right? So they can't get heated up at all. And like, just, it doesn't strain the imagination much to imagine how when things get really cold, you start getting little droplets of stuff, right? You see this on a cold, you go outside, you can see your breath actually start to make little vapor droplets, right? So the gas molecules, the water that comes in a gas form out of your lungs at temperature gets cooled down and condenses with other little molecules, and you start getting these little tiny droplets. That's why you can see your breath when it's cold outside. Same kind of thing could be imagined very easily to be happening deep inside of these clouds in interstellar space. And once you got little droplets of stuff, well, you're off to the races, basically. The old leaning on gravity to do all of the work for you, it sort of falls short of explaining things for me, particularly in light of the fact that most clouds that we see in space are kind of blowing apart on their own, just like you would expect if you popped an enormous balloon full of gas in outer space. You wouldn't expect the gas to just come back and form a balloon all by itself. That kind of strains the imagination. I don't know if that answered your question, but I'm doing my best. Is that all right? Okay. Yeah, Michael.
Well, I feel like whatever the event is that caused the gas cloud, you probably got like a bunch of ions in both directions, but they're a little bit too far away to interact, and just eventually, because they're, we'll say close enough to each other, they will start getting close enough to interact, and then they'll start condensating because they're finally close enough to react with each other.
Yeah, I think that happens.
And then they start getting a mass to gravity, and it's like a runaway reaction. Like a lot of
Yeah, I think that's probably closer to what's happening, definitely. And so it's been I think this has changed in the last year, as far as I can tell. It's really interesting. I was just looking at my notes from last year, and then I was kind of just going through the literature. And sometimes I like to, I'll talk to like some of these LLMs, like ChatGPT or something like that, and just try to find out exactly what like the state of the art is, because it's pretty good about telling me like what's the latest literature on some subject. And it's really interesting to see it change from year to year, how fast all this science is being updated. It's really wild. I feel like we're making incredible progress at a speed that's, hasn't happened in a century. Pretty crazy stuff. All right, what else, guys? Yeah, Diane.
About the Earth density,
We'll talk more about that today.
that we talked about last time. Why did rocky planets like Earth from in the outer regions of the solar system rather than in the sun?
Yeah, that hurts the head a little bit. So she's bringing up, I kind of previewed what we're going to do today, which is how do you get planets made. But one of the most bizarre things, I was actually grilling ChatGPT about this before class, just to make sure that people actually really think this. But yeah, how do you get the most dense object in the solar system to form outside of the center of mass of the solar system? It's a really interesting problem, actually, the deeper you get into it. And there's some complex attempts to answer that. And once we see how the standard model of solar system formation unfolds, we'll see kind of what arguments are given for how these really rocky planets could form essentially in place where they're at. But I think there's a more appropriate answer to that question that involves the evolution of planets. And so I'm going to make that case for you as well in just a few minutes once we get cooking. So hang on to that thought. We'll answer it, or we'll try to anyways. What else? David?
I thought the Eagle Nebula was cool. I thought it kind of did look like the back of a horse's head.
It did. It did.
And I thought it was cool when we were talking about absolute zero and how it's like the atoms are basically not moving at all, and how the pockets inside the, say like Eagle Nebula are pretty much 10 to 20 Kelvin above absolute zero.
It's just basically nothing. Yeah. Yeah, I don't think anyone's ever achieved absolute zero. I think they might have been. I don't know. It's hard to tell. If they did, they probably squeezed. They probably squished an atom really hard with lasers from all directions and made some argument that it was standing still. I don't know. That's an interesting way to go about it. But yeah, 10 to 20 Kelvin is really cold. So you can imagine that these molecules and these atoms are basically not moving. They're very likely to, I wouldn't go so far as to use the word ice, because ice is a problematic word, but you can imagine them aggregating in interesting ways when they're not moving. A lot of what makes atoms bounce off each other is heat. So you take the heat away, you're in a much better position to get local dense regions. So yeah, there seems like there's a lot of ways to make locally dense regions. It's not as troubling. It's the least troubling part of the entire story for me is how these stars form. But we got plenty of problems in other domains that we'll deal with. Planets are a big problem, as far as I can tell. Just like not all planets, but particularly the rocky ones. They're really, really weird. They're really, really, really dense. Our planet's about 5 times as dense as the sun on average, so that's pretty crazy. Yeah, extraordinary evidence requiring extraordinary explanations. So we'll get to that. Anything else, guys? What else? Yeah, Kai.
Do we know if the chemical compositions of nebulas change, like where on the HR diagram the star will end up? Like, do we know if this nebula contains a certain amount of hydrogen or other chemicals, then it'll be like a red giant or a white dwarf?
Yeah, so the giants and the dwarfs are actually part of the death phase of the story that we haven't even hit yet. That's what they're thought to be anyways. Of course, they're all just theories. But the best thing that I can answer that with is the more stuff you have in one place, the more dense it is, the more likely it is you're going to get a bluer star out of it, right? Because the more stuff, standard theory would have it, and I think this holds whether you choose a gaseous or a liquid sun. The more stuff you have in one place, the hotter it's going to burn, basically. For lack of a better word, the hotter it's going to fuse. Just its surface temperature will be bigger. It's going to have a bigger surface area. So, most of these stars, like almost all the stars, are essentially made out of the same stuff, which is really confusing because their differences largely come down to, how much of that stuff is in one place. If you have too much stuff, by the way, your life's gonna, your star life is gonna be very short because you're gonna burn through. You're gonna have too much pressure. You're gonna be overpressurized. You're gonna burn through all that material really fast. So, the biggest stars are thought to be some of the shortest-lived stars too. So yeah, it definitely sets up your fate depending on how big of a cluster, not necessarily the size of the cloud overall, but how big that local dense region is. And I'm sure chemistry is going to play a huge role in it too. So the details of what causes you the details of what causes a particular region of a cloud to be denser than another region, those are going to probably be enumerated the more that we understand like the chemical processes, the shock wave processes, all of these different ways of concentrating material in one place. I mean, it's a lot easier to you know, how would I put this? Liquids are already way denser than gases, right? So if you get condensation reactions, it's pretty easy to start getting something really dense, even at the droplet form. So it's very hard for me to just naturally have a naturally occurring little pocket of gas that's really dense. That strains the imagination for how that would happen. It's very easy to do that with condensing liquids, essentially. You get droplets, they form naturally, which are, you know, really just a cooling reaction. It's a chemical reaction, but it's a natural process of cooling. So, yeah, you could imagine just really, really cold parts of deep inside of these clouds might be able to condense huge volumes of liquid hydrogen, essentially. And you get something, you do get big enough drops, you could probably start to then gravitationally attract a lot more stuff to you, including heavy metals and stuff. So the way that, you know, a lot of the heavy metals, right? Like we have a lot of metal in our daily lives. That stuff's not even necessarily thought to come from fusion reactions per se in stars. It's actually supposed to, the only pressures that people can imagine that would be possible to generate those huge metals are actually in these violent explosions called supernova. So we'll talk about how you get these really heavy. So then ultimately, as those stars are exploding, they're making little blobs of metal, and those could get incorporated into the new forming stars, right? And then as they live their lives out, maybe they explode. Maybe there's other ways besides exploding that they could give off metal too. I will play with this later, but yeah, the lives and deaths of stars seem to depend much more on how much of the stuff gets glommed together than exactly what type of atoms it is or anything like that. It's a good question. Anybody else? Any other thoughts? Yeah.
Can I give you my theory on internal return?
Yes,
So
please.
Here's
Nietzsche.
how I have it in my head.
Okay.
So think of it like at the end of, I guess.
Wait, can you remind people what it is really quick too?
Right. So eternal revolution or eternal return.
I think it's eternal recurrence, or it's a translation of German. So
something, and then it's essentially time repeats itself in an infinite loop, and everything that will happen has happened forever and will continue to happen. And so essentially, I'm like, why would the universe itself have this sort of like fail-safe to reset? But the way I think of it is like it's not built in the universe to do it, but the like species that evolves so far into the future enough to where like they don't have to eat, they don't have to like use the bathroom, and like every answer they have is solved. So like essentially, it's like there's no room for any more evolution. So it's like they can't just like de-evolve without like wiping their memory. So they would just have to like they would have some sort of technological advancement to be able to pull that off.
you think because they'd get bored or something?
Or because they essentially yeah, they kind of lose their mind because they don't have like any purpose anymore. Like that illusion of purpose is gone. But that's how I would rationalize it.
Interesting. Yeah, I mean, I think Nietzsche's argument is just that like the universe just runs out of possibilities at some point. But yeah, the future of human beings that have everything they ever wanted is a really interesting problem to solve. It's actually kind of playing out right now. I don't know if you guys noticed, but we're like unbelievably rich compared to 99.99% of our ancestors. We have a really nice warm room right now, and we have a dining hall to eat dinner at, and it's actually resulted in a lot of interesting problems for people to have all their needs solved. Because for most of human history, like you didn't have crisis of meaning because you're just trying to keep your family fed for the most part and keep your house warm, which is a full-time job as far as I can tell prior to this industrial age. So that's a serious, interesting crisis for people to solve in the future, the easier we make it for ourselves. I think it was Nietzsche, was it Nietzsche? Or was it Dostoevsky? One of these absolute mega minds pointed out that, if you give, in the future, if everybody had everything they wanted, they would just start breaking things so that something interesting would happen, which is kind of a scary thought, but kind of makes sense too. I think little pieces of that play out, people get into these dramas, and I don't know, people need problems to solve. So having all of our problems solved is not necessarily the best situation. What do you guys think? Yeah, Brooke.
I don't think we can run out of problems.
Okay.
In the fact that if we're suffering of having no problems, there's clearly still something wrong. And I think that if there was really nothing wrong, that wouldn't be an issue.
Yeah, I think I'm kind of with you. I feel like, a tangential issue to this is people being like, well, AI is going to take all of our jobs away and we're not going to have anything to do. I'm just kind of like, people have said that at every age of technological development. They've always said, that this new technology is going to remove everybody's work. But people always find new work to do, right? And especially if you're into any kind of art or creative work, it's a never-ending process. You're never going to do that one painting that's the best painting ever and then just quit and retire, right? It's you're always kind of chasing that dragon. So yeah, I don't know. What do you guys think? Anybody? Thoughts? You guys worried about AI taking your jobs? Anybody? Nah. That's interesting. Nobody's worried about it. A little bit? What kind of work are you trying to get into?
Graphic design.
I wouldn't worry about it.
I'm not super worried
yeah.
about it happening soon, but
I mean, you'll have to definitely learn all those. You'll have to definitely figure out how to use it. People are really allergic to just, kind of like hack job AI artwork. I think that's kind of unappealing, but I don't know. What do you think? Yeah.
I think people overestimate how good AI is.
Yeah.
It still makes a lot of mistakes.
It's pretty stupid sometimes.
It isn't as good as people think it is.
Yeah. I don't know, and it's not clear that that's going to change either. I'm not sure. What do you guys think? Is AI going to displace anybody? Think? Anyone want to make the argument AI is going to displace our our intellectual work off the planet? Yeah.
we actually did a whole lesson and stuff in my educational technology class
Cool.
about AI and when to use it, when not to use it in the classrooms, and just how it can be useful at times.
Yeah. Cool. I think I'm going to make it part of your final project, actually, because I was thinking it's actually so important. But I'll tell you more about that next week. I'm still a little half-baked on it, but I do want it to be a part of it because, times are changing for sure, and I think you need to figure out how to spot AI when it's being dumb and then how to make the best use of it at the same time. Yeah, Mia.
I'm going into education and I'm less worried about it taking over my job and more so of it diminishing the uniqueness and individuality of the students. If they're constantly relying on it, then they're not forced to be creative, and that's I think one of the biggest tools that humans have is the creativity.
Yeah, I was talking to this professor the other day, just doing a pre-show meeting for the podcast, and he was talking about he had this way around it because he'd always been asking students to write essays for his course. He was teaching I think it was a biblical archaeology course or something crazy. And he determined that this year what he was going to do was he was going to, instead of just giving students the question that he wanted them to write the essay about, he would give ChatGPT or some LLM the same question and then give the students the essay that the chatbot wrote and then be like, what's wrong with this essay, actually? Which I thought was really smart, actually, because the chatbots, they do make mistakes. And I think learning how to recognize those mistakes is in some part going to determine your ability to thrive in an ecosystem that's dominated by those. And knowing how to actually steer them intelligently is huge. That's a really useful skill, actually. Did you have something in the back? Yeah. Antonio.
I'm a computer science major, so I feel naturally I'd be worried that we're taught
Yeah, it seems like it needs a driver still is the thing, right? No one's ever made the case to me, and I've talked to a lot of AI researchers. I got a lot of friends down in Silicon Valley who are doing this stuff. I've never been convinced that there's any sign of these things being able to self-prompt themselves into interesting curiosities. There's a curiosity gap, right? There's something really interesting about the way our minds work that's different than whatever the heck is happening behind the code of these machines. We're very curious. We really want to identify inconsistencies in our own knowledge base about things and rectify them. And there's nothing, no glimmer of that in these LLMs from what I can tell. Yeah.
Like my composition class just got finished with like not even finished. We're still talking about AI and like creativity.
We'll never stop you.
versus, like the AI's creativity.
Cool.
Like there's a millionaire AI artist called Plotto. Which
Okay.
even then, like it needs like prompts to
Yeah.
generate its art, and like it takes like pieces from public pieces of art, and like it doesn't really obtain our special ability of like having creativity and stuff. And it has like a neural transmit thing where it's like based on our brain and like stuff that still doesn't obtain that ability to come up with dumb stuff.
Yeah. Yeah, that's the final frontier. I mean, if I see some hint of that, I would definitely be thinking about this a little bit differently. But I think there's something really special, much more special than is obvious on the surface about the way that our minds work, that isn't accounted for in these machine processes. Had a really interesting conversation with a linguist about this too, because the case can be made that how we organize our thoughts is largely through language, and the way that these things do language is very different than the way humans do it, right? It's kind of a fill-in-the-blank sort of algorithmic approach, whereas we're really trying to link together, curiously, inconsistencies in different concepts or consistencies in order to kind of make efficient new concepts. It's just a very different way that our heads work, I think, than these machines. That's not to say that somebody couldn't come along with a genius idea of how to make better LLMs or better artificial intelligence in the future. I'm sure this isn't the last rodeo, but for the moment, I would say learn how to work them. Learn how to work them and develop your creative side, because that seems to be one element that these things can't do. But super useful for everything else. Like I always used to hate coding a lot, and I had to do it in grad school, to make different robots do different things for my project. And I'd always have to go and make friends with a guy who was really good at coding and be like, come on, man, help me with this, because I can't get my code to work. Now I can just go to ChatGPT and just be like, hey, write me a code for this in this language, and it's done. And I didn't have to learn anything to do it either. So it's super useful, but it's not going to come up with an idea of what I should code in the first place. So interesting stuff. All right. Should we get on with planets? Any final thoughts? I love hearing from you guys. It's half the reason I'm doing this job at all. It's nice to see what the young minds are up to. Planets. So planets, this is where things get a little bit spicier, I think. And I think there's some really interesting work going on. So, there's two ways that I can talk about this. I want to weave a little bit of mythology into this as well as we go through it. So, planets have always been a very perplexing thing to people. So when folks first started going out at night and staring up at the sky, most of the stars are in the same place every night. At least every season they're in the same place. And over tens of thousands of years, there's some shifts in that. But over the course of a lifetime, if you go outside at night, you're going to more or less see the same stars in the same place, except for a few of them. And those, to people prior to industrial telescopes, those would have been the planets. And people didn't really think of them as different than stars, except for the fact that they did weird stuff. They were moving around. Not only were they in different places every night, sometimes they would go backwards, right? So, Mars, famously, it moves backwards sometimes. So what the heck was up with that? And naturally, I think it's a pretty reasonable conclusion. If you see all the stars more or less fixed in place, but some of them are kind of doing what they want, what do you conclude? I don't know, that the thing has a will of its own, perhaps. It's doing what it wants to do, which is, there's plenty of things like that on Earth, right? So it's a reasonable conclusion to have about the sky. So the Greeks called these things the wanderers, which is really what this word planet comes from. It comes from the word to wander, because certain stars seem to be doing something bizarre. And they focus their cosmology largely around these planets too, because they seem to be the animated ones. They represented their gods with these planets. And it's interesting because we still call the planets by those god names, right? So Jupiter, sort of the patriarchal deity of the Romans. The Greeks would have called him Zeus. Mars, the god of war, right? And so what the heck is this all about? These pagan religions often get a bad rap because people think of them as like overly superstitious and, what the heck? Like, why are there all these warring deities and like, where do you get this from? But I think that there's like a much more generous interpretation of the way that all these ancient peoples described their pantheon, which is comes down to the work of Carl Jung. Has anybody read Carl Jung or know who he is at all? Oh, great. Well, you all should. There's a few really important thinkers in this space, and Jung is one of them. And Jung was thinking a lot about these ancient, because a lot of the ancient religions were these very pantheistic, lots of different gods for all these different things. And he started realizing that, I think each one of these gods is actually identified with something like a prototypical or archetypical experience that we have. So, Mars is identified with rage and war, right? And archetypical emotions like rage are interesting because they're sort of like things that you know how to do without anybody telling you how to do them, right? So if you think about the subset of things that you essentially can pull off pretty well without anybody showing you how to, it's like rage and anger, so Mars, let's say lust, Venus, all sorts of these prototypical emotions that are associated with these different deities that we associate with stories and around these planets. And it's been so important that we preserve the naming structure all the way to this very moment. So the sort of Jungian interpretation of the pagan religions is more like these people were celebrating these, the way that our minds are constructed, essentially. Now, modern neuroscientists might call it like the limbic system or something like that, right? The emotional centers of the brain. But, when the Greeks would have said, you've been like possessed by Mars or something like that, you could say today that, yeah, like your limbic system was overrun and your amygdala displaced, your prefrontal cortex and overran your personality and you did something stupid and punched a guy at the bar or whatever it was. But the way that that these ancestors of our Western tradition, going back to Greek and Sumeria, were thinking about it was encoded in their mythological structures and encoded in the gods that they essentially named the planets for and told the stories on the tapestry of the night sky. So that's something to keep in mind with this. There's something really profound about the fact that we kept the names of all of these, right? And even when we go to new star systems, we often name them after these Greek gods still, or after myths that have long since disappeared from our mainstream culture. And so you got to kind of ask yourself, why is that still so important to us? And I think it's because there's something really deeply meaningful about it as well. So, okay, that's planets for you. So we got a few little pieces of the puzzle because we want to say we want to come up with a good set of hypotheses for how planets are made today. I set this up last time that there's some challenges. So in this nebular collapse model that we've been talking about, whether you take like a liquid or a gaseous approach to it, at some point you have this nucleation, you have over density, you have a star which is formed through the processes we talked about last week. Planets are a little bit more tricky because now that you've got all of this stuff in one place, the standing theory was that out of that, more bodies would start to nucleate. In other words, we talked about this process last time as this T Tauri star starts to collapse, it's spinning really fast, right? And it's kind of ejecting dust in its wings. It starts to form this little disk around it. And in that disk, you can imagine that the solar wind is crashing against the disk of dust. And so there's some over-density regions in there that you might be able to imagine pressurizing a system enough to get the nucleation of new bodies like planets. That story is very, very, very old. So actually, this basic idea of the nebular collapse was created by this guy named Emanuel Swedenborg in 1734. The philosopher Immanuel Kant helped him develop it along with the mathematician Laplace. And that basic idea of this swirling nebula collapsing down has been popular all the way up to the present moment. And that is essentially the standard story that is told about the birth of the solar system. There are three really big problems with it. I previewed them for you last time. One is the angular momentum problem. So why is it that Jupiter is got all the angular momentum in the solar system and not the star at the center? Because remember, our birth story has all this mass congealing on one point, and it starts to spin really fast, right? Just like the figure skater, when they bring their arms in and all their mass is concentrated at the center, they spin really fast, right? So why in the world is all of that spin energy in the planets, especially the ones that are really far away? I think Jupiter is like 30 times the distance between us and the sun away from the sun. It's really far away. So why is all of the spin energy over there? That's the first interesting problem. Second interesting problem I've talked about a little bit today, which is the density problem, especially of the rocky planets. That's pretty weird. Why in the world isn't the dense stuff in the center of the sun? Certainly a lot of dense stuff is in the center of the sun, but why isn't it all there? Why are there big chunks of rock that aren't in the center? And then the fourth problem is sticking together pebbles, right? Sorry, third problem. How do you stick together pebbles, right? Pebbles tend to, you might be able to get little pieces of dust to stick together. You might be able to get little droplets of stuff to stick together. But how do you get little chunks of rock to not just bounce off each other in this disk in which these planets are supposed to be sort of accreting? So those are the troubles. That's the general overall story, which has been around for 300 years, is this nebular collapse idea. And then, what other approaches might we take to solving that problem in the future? So let's look a little bit closer at the details of it. This is another piece of the puzzle that's made this a lot easier for us lately. And the reason that we're even anywhere close to being able to solve these problems is because we're finally able to see other solar systems. You guys might not realize it, but before about 10 years ago, we had almost no data on other solar systems. And you go back 20 years, 25 years, we had no data. So this story that, Swedenborg and everybody since had been developing about the formation of a solar system was entirely based on one solar system. So in science in general, when you want to make a statement about a generalizable statement, right? Like, I don't know, about how creatures evolve, let's say. You probably want to look at a lot of different creatures, right? You probably don't want to just study like one snail in a jar and try to make a statement about all animals everywhere, right? And so, unfortunately, all we had was one snail in a jar for 300 years, and we have developed this nebular collapse model for how this works. Fortunately, we got exoplanets now, which is super exciting. So we'll look at those a little bit and see what we can learn from them. Spoiler alert, most exoplanetary systems look nothing like our solar system. And so that was extremely illuminating because, oh my goodness, we're kind of the odd man out, and things don't seem to have happened the way that they happened here necessarily. Okay, so let's check it out a little bit. So one kind of interesting thing is that like seeing a planet is actually really, really hard. As you can imagine, they're very small for the most part. You know, planets that are far away. I'm not talking about our own solar system, but seeing a planet in another solar system, especially one forming, is really, really, really hard. Primarily because they don't have much surface area, and they're not that hot. And we can only see things either with light, like they're not giving off much visible light, if any. They might be reflecting some or screening some out from a star. We'll talk about that. But they're really little and they don't have much surface area, so they're not glowing very much. Even if they're giving off infrared light, it's not very much because their surface area is really low. Fortunately, we do see a lot of these disks. Now, disks actually, it turns out, if you can imagine, have lots of little dust grains in them. And so if you think about surface area, the more dust grains you have, you're actually multiplying the surface area much faster than you are with something like a planet. So we can see with infrared telescopes, we can see a lot of these disks around what will become or are already stars that have just been born. So a lot of the early work done on this moment and people hoping to find planets actually being created is done by looking for these planetary disks, these kind of nascent areas where we might actually hope to see something happening. Now, of course, making a planet takes far longer than you can sit around watching one of these disks, and so occasionally we'll see something that we think are planets, little regions of high density inside of these disks, and then we try to peg that to our story of the creation of these planets. But we can't actually see them happening in real time. So this is just a few examples of them. What else do we want to say about these guys? One of the things that's kind of interesting is that as you do get planets starting to appear inside of these disks. So, you know, there's really two possibilities, by the way, when you're talking about how to make a solar system, right? You either make those planets right there inside the solar system, or you get them from somewhere else, right? In which case they had to have been made somewhere. But we see these interesting ring structures start to develop, actually, where it's thought just like in Saturn's rings, kind of similar thing happens where there's little moonlets in Saturn's rings that are sweeping out regions in between them, so you actually get separation of the rings. It's thought that planets actually sweep out the little voids in between these ring structures in these protoplanetary disks. Again, it's very hard to separate out whether something was captured into this system or whether it happened right there inside of it. Of course, the standard model that's been pursued for a very long time has us creating these things exactly in place, more or less where they are. And there's some details to that which we can talk about in a little bit. You guys have a question?
No.
Oh, all right. Yeah, what's up?
Isn't the definition of a planet like it has to clear its orbit?
Yes. Yes, exactly. Yeah, so that's definitely, so if your story, so if you see an object like this out in deep space, well, naturally, you can explain it using that model where it swept these orbits out. Real question is, where did it come from? Did it condense out of this ring? Was it snatched up? So there's another piece of this puzzle which is really just come out in the last couple of years that's really fascinating, is that we found these free-floating Jupiters orbiting each other out in the Orion Nebula, right? Not just a couple of them, but like 40 pairs of them in the first weekend that they were doing this particular telescopy project, right? So what the heck are these Jupiters doing orbiting each other? Now, the most popular theory is probably that they were thrown out of solar systems while these solar systems were in this stage of being formed, that they formed like little droplets orbiting the star, and then they were kind of cast out. But an equally valid hypothesis, which is still seriously entertained, is that no, those Jupiter-like planets actually formed just like stars form, right? They actually condensed out of those giant clouds, just like a star would, except they didn't have enough condensate. They didn't actually get enough material together to make a star, which is really, really interesting. I think that, and by the way, I don't think either one of these hypotheses is necessarily exclusive of one another, right? At least in my mind, it seems like you could perhaps condense or accrete a Jupiter-type planet, a gassy, they're not actually made out of gas, by the way. We call the gas giants. They're not made out of gas. Nobody thinks they are. They thought that originally. They're actually a form of liquid as well. So, you could have both actually work out. You could have Jupiter-like planets that are condensing out of these giant molecular clouds, same as stars, and you could, potentially have them condense out of this disk that's forming around the stars as this debris is piling up in their circumference area. So neither one of these seems to be necessarily at odds with each other, but they're two really interesting possibilities, and no one would have ever thought prior to a couple years ago, there was no evidence that Jupiters could form by themselves without a solar system. In fact, there's no evidence that any planets could form without a solar system. So, we should expect that idea to be making its way very slowly into the narrative that we're telling here. Do they talk about those free-floating Jupiters in your guys' textbook? Anybody remember on this chapter? I have to check it out. I don't think they do, probably. It's brand new stuff. All right. Okay, so, like I said, maybe about 20 years ago, we saw the first exoplanetary system, which I think, that was one of the biggest leaps that we had in our understanding. This is actually that system. Now, what's really nice, and probably why this was one of the first ones discovered, is that it happens to be facing us head-on perfectly, right? So we can actually see the planets going around the star really nicely. If the thing had been turned on its side, it would have been a very different situation, and we'd have to use different methods to check it out. This is a planet. This planetary system does not have a cool name. It's just called PSR 1257 plus 12. All right. What else do we want to say about that? Most exoplanetary systems that were done after that, and sometimes we'll get a nice picture like this still today, but most of them come down to looking at techniques where the planet is exerting, we detect the planet wobbling in a really interesting way. And we talked about this with detection of the white dwarfs previously, and I'm going to get back to white dwarfs very soon. But most of the ways that we detect planets, exoplanetary systems, is indirect. It's gravitational effects on the host star, or the planets going in front of the star causing it to dim. So very different than actual direct observation of these things. One of those methods is a kind of Doppler shift method, right? So if you think way back to the beginning of this course, we talked about this radial velocity method, where you can see the stars as they're kind of moving away. The light is going to shift a bit towards the red, and as it comes back around, it shifts a bit towards the blue. You can do a very similar method with the stars to see how the star's position is changing, which will actually in turn tell you about the little tugs that are being exerted on it by the planets. So this is actually being done on the stars themselves, not necessarily on the planets as they go by. So the first time they used this, I think, was in 1995. This was an indirect method. This is prior to actually seeing the planetary systems themselves, which is crazy. I don't know. I actually remember 1995. So this is really new stuff as far as our understanding of the solar system goes. This was in the constellation Pegasus, which, by the way, Pegasus is a really interesting mythological creature. You guys know about Pegasus at all? Yeah? What do you know about Pegasus?
The winged horse created, I believe, by Poseidon.
Nice.
Very freaky mythology.
what do you think Pegasus represents? I think Pegasus is associated with with inspiration. So like the kind of messenger between different experiences, essentially. There's something really, really profound about inspiration as a human emotion, which I think is one of the most peculiar and interesting emotions, and certainly a thing that these AIs don't seem to possess in any capacity. And Pegasus, in a sense, represents that. It's this ability to link different things in the mind, right? So this winged horse would like flutter between these different gods, and later on, like Hermes, associated with Mercury and the winged foot and stuff like that, is also associated with inspiration. But yeah, inspiration is a really, really crazy emotion. All right, so that was the first detection using this method. There's the problem with this method too, which is that are you going to be able to see? Would you be able to detect Earth using this method if you were, I don't know, 100 light years away? What would you see if you used this method on our sun to see our sun's wobble? Like, what would you see? Anybody? What if I told you that Jupiter has most of the mass of all of the other, it's got most of the mass of the planets in the solar system? Yeah, that's right. Yeah, so you would probably be able to scope out that we had one really big planet in the solar system. And that's about it. So actually, the wobble associated with Jupiter is so large that the point that Jupiter orbits in the solar system is actually outside of the sun. So the sun and Jupiter orbit each other at a point slightly outside of the surface of the sun. So the method's pretty good, but it's reliable, but it has a selection bias. You're only going to see really big things, actually. You won't be able to see small stuff with it. And actually, most of the indirect methods that we have are going to have that same selection bias. And selection biases are really tricky. They crop up in almost every science. It's very easy to see the things that are obvious and very difficult to see things that aren't lit up well. It's no more a problem than it is. It's a huge problem in astronomy of all disciplines because all we have is light at the end of the day. There's a similar method here where we can actually look at how when a big planet passes in front of a star, it actually dims that star a little bit. Again, suffering from the same selection bias that we're only going to see huge planets. So these methods are cool, but they're not perfect, and very rarely do we get a beautiful direct detection like this kind of thing. So let's see. I wish I had the dates for these. There's been two really huge telescope projects to look for exoplanets. The first one was this TESS project. And TESS looked in every direction, but it only looked out to, 200 light years, which is actually really, really far. But it looked all over the place. The more modern one is called Kepler, and it's searching for 3,000 light years, but it's only in a tiny little window. And they've detected thousands of planets. So let's look at what's coming out of that Kepler project. So this is an interesting spread. This is basically planet size versus how long it takes to go around its star, its orbital period. So that's kind of like its year. And it's all normalized. This is days down at the bottom, and size is relative to Earth. What do you guys see there that's kind of interesting? Anybody? Yeah.
That in the one sense Kepler, they're a bit more just before Kepler, but there's just a few outliers where Kepler seems
Yeah, what do you think about the clustering? Yeah, so there's probably something like that, right? So there aren't that many that are Earth-sized or smaller that we've seen, right? It's going to be pretty hard to see using any of these methods we've been talking about, it's going to be basically impossible to see anything the size of Mercury, right? A little tiny planet. Mercury is, about the size of our moon, for instance. It's pretty little. So it's going to be hard to see things that are bigger. But what is kind of interesting is that most of the planets are somewhere between the size of Earth and Neptune. That's really interesting, that the most common type of planet would be a planet between the size of Earth and Neptune, and we don't have any of those in our solar system. I think this was completely shocking to scientists at the time, actually, because they'd been studying our solar system exclusively for 300 years, and we had this whole story of how the planets formed and everything, but we didn't realize that we were missing the most common type of planet, which is, depending on who's talking about it, they'll either call it a mini Neptune or they'll call it a super Earth. Generally, the mini Neptunes have a little bit bigger atmosphere. So that's pretty crazy. So most of the planets that we're seeing are bigger than Earth, and they're smaller than Neptunes. And, still have some Jupiter mass planets, some that are slightly bigger than Jupiter mass planets, but there you have it. So that's pretty interesting, and there's quite a spread of those super Earth / mini Neptune planets as well. I'll give you a different way of looking at it. This is like a bar graph, like a histogram, where you essentially count how many of each types of these planets was coming out. Now, you also see this is basically our solar system up at the top, the different types of planets that we have. So, there's a fair amount of ones that are close to our Earth size, but the most common types are completely missing. Then you have some Neptunes, some Uranuses, you have some Jupiters, so on and so forth. This is a brown dwarf over here, I assume. Okay, so what's going on with that? It's really, really, really interesting. This is probably one of the fields that I've seen the most amount of research coming out about trying to explain this situation. First of all, why don't we have any of those? Second of all, why are they so common in the universe? So, a lot of the, so I'll give you one more piece of evidence to kind of round this story out. One other thing that they've seen, which is really quite interesting, is in other solar systems, let me back that up. In our solar system, the really big planets like Jupiter, I already mentioned Jupiter is super far away from our sun, right? Really, really far. It's really cold out there. The things that we used to call ice giants, they're not really made out of ice, but the name stuck. So Neptune and Uranus, they're even further away than Jupiter, right? It's really cold out there. So for the longest time, people thought that the only way to develop these giant planets was essentially in the really cold part of the solar system, where you can actually get the condensation of these materials. Otherwise, really complex molecules that we see inside of Jupiter and Neptune and Uranus, they would be destroyed by like by the radiation from the sun. It'd be too hot. But recently, we've started finding these really weird cases where there's Neptunes and Jupiters right next to a sun, which is crazy. Nobody thought we were going to see that. And what's happening to those planets that are right, those Jupiters and Neptunes? They are often moving fast. What do you think is happening to them, though? What happens if you put a snowball next to a heat lamp? So they're getting their atmospheres blasted off. That's what's happening. So those they call these things hot Neptunes or hot Jupiters. They find them often very close to the stars. Now, the story for how in the world they got there and what's going on, of course, almost everything you can imagine, people have tried to throw at it, and these often involve steps where they're formed really far away, and then they drifted in, and then maybe they'll drift out again, and there's all these migration theories about how this can happen. But needless to say, the planets, these huge giant planets that are close in to the sun, they're changing. They're I don't know if I want to use the word evolving necessarily, but they're metamorphosizing, sort of like a caterpillar into a butterfly. They're changing very rapidly. And so what happens as the planet starts to lose its atmosphere, like a Neptune or a Jupiter? Well, what's really interesting is that based on a number of different features, but a lot of this work's been done on density, we know that Neptunes and Jupiters and Uranuses have a solid rocky core at their center, actually, right? So what happens, and how people are starting to explain this radius gap, in other words, this missing gap, like why don't we see these things, is because these planets, as they start to lose their atmosphere, at some point, you get into a feedback loop where once you lose a bunch of your atmosphere, then you don't really have the gravity to hold on to the rest of your atmosphere like you used to because you've gotten a lot smaller. So it accelerates the process. And so planets will go through this period where they'll lose their atmosphere really, really quick. And I'm talking about huge atmospheres, like an atmosphere like 10 times the size of the radius of the Earth would be piled onto something like a Neptune originally. And as that thing, if it spent any time near the star, it would lose that atmosphere and it would get cooked down essentially into something that started looking like a super Earth. And as that super Earth continued to evolve, maybe it was even able to migrate out of that dangerous region, but it still wouldn't have the gravity to really hold on to its atmosphere for that much longer, and it would change. So this is completely radical. People have actually, this is a Nature paper that came out 2 years ago, where people started applying this idea to the Earth itself, that maybe in the past the Earth actually had a giant hydrogen envelope, a huge atmosphere. And as a result of that, the atmosphere being cooked, you actually were able to generate the oceans as a result of it, which I find really, really intriguing for a number of different reasons. I'll put a couple on the table for you. But I don't know about you guys, but when I was like 5 years old and I asked my parents where the oceans came from, and they told me that we got hit with a bunch of comets, I was like, really? Like, it just didn't sit with me very well. And so there's been a lot of interesting work about water and the presence of water and where our oceans came from. Obviously, condensation reactions in chemistry make a lot more sense than getting hit with a bunch of comets. I don't know if you guys ever been to the ocean before? A lot of water. There's a lot of water. Turns out that scientists are now figuring out that minerals under our feet, the rocks in the crust, in the mantle, they actually contain water, which is not necessarily in a liquid form, but it's bound up into the molecules electrostatically. It's actually the rock molecules can actually bind water in its pockets, and they think there's something like, anywhere between 1 ocean to 6 oceans worth of water under our feet, just sopped up in the rocks, essentially. That's a lot of water. So if the ocean is a lot of water, just think how much water could be tied up in the minerals. So those are all chemical processes that would result in that water being tied up there. So this is interesting. The fact that you have a huge population of planets who are somewhere between Earth and Neptune, the only difference really being how big their atmosphere is. I mean, quite frankly, the only difference between Earth and Neptune is that Neptune has an enormous atmosphere. Enormous, right? In our solar system, we don't have those. So the question becomes, why don't we have them? Well, is it possible that the reason we don't have any of those many Neptunes or super Earths is because we used to be one of them? That's an interesting possibility. It's interesting also because when you have an enormous atmosphere like this, you're really massive, you have a ton of gravity, which means you have a ton of pressure available to squish rocks together at your core and make something that turns out to be the densest thing in the entire solar system, which is what we're standing on right now. So you have an actual mechanism by which you can achieve something like this incredibly dense rock that isn't inside of the middle of the sun, where it should be if they all formed together at the same place. So I think that's a really, really interesting piece of the puzzle. There's another piece of this puzzle too, which I'm not entirely sure what to make of, and I'd be curious what you guys think. Scientists study all these exoplanetary systems from Did you have a question? Okay. Scientists study these exoplanetary systems, and they basically group them into 4 bins, right? Whether they're ordered, so like the littlest ones out to the biggest ones, whether they're mixed, so kind of a hodgepodge, whether they're all the same size or not, and then anti-ordered, so the big ones interiorly out to the littlest ones. And the results are kind of shocking. So these are simulations and also actual data. The orange is the data. So this bar off to the right over here. What's interesting is the similar ones and the ordered ones seem to be the most common. And I'm not sure what to make of this exactly, but we obviously in our solar system, maybe not so obvious, but David took the class last semester. We went with excruciating detail through all the different planets. We have neither a similar system nor an ordered system. It's a little bit crazy, which to me speaks to us having a really interesting past that isn't quite as simple as planets formed right here where we thought they formed back in the beginning of the solar system and stuck there. And I'm simplifying the standard story a little bit. There are some migrations of the gas giants that people have been theorizing about for 50, 75 years. But generally speaking, the story that's told in your textbook is one of the planets more or less forming in place, particularly the rocky planets, and living out their lives to the present moment. But something else is happening in these other solar systems, or something else is happening here that we don't see as often in these other solar systems, which is really quite intriguing. So oftentimes we'll just see most of the solar systems we see just have a ton of these super Earths or mini Neptunes just hanging out, right? Sometimes we see one getting its atmosphere cooked off. I just actually saw a first report of something they called it I think they called it a giant Venus. But it was basically this carbon-rich atmosphere, some sort of carbon monoxide, carbon dioxide atmosphere that was getting cooked off because it was too close to a sun. That's really interesting too, because Venus, the story that we tell about Venus, it probably stands to be updated, right? It has a very thick atmosphere still, but nowhere near the size of a Neptune or anything like that. It's just very dense. It's actually quite shallow. So the fact that all these planetary types can undergo these transitions, these photoevaporation transitions near their stars, is really, really tilting the story about the formation of planets towards something, this is a huge debate in science right now. But in my estimation, it's really tilting it towards a metamorphic story where planets, don't spend their whole lives looking just like one kind of planet. They might spend different portions of their lives as different types of planets, which is really, really interesting and exciting. It also makes the story of our own solar system wildly complex and convoluted and probably full of chaos and disasters and things that we try to avoid building into our really nice uniform stories of how things happen. Disasters, changing orbits, all that stuff's very uncomfortable to us for obvious reasons, because it would be really nice if everything was just chill and static in the long run. All right. I think these are the main things I wanted to hit with solar systems. I could keep going, but concerns, questions, anything pop out? Yes, please.
We were talking about all the planet stuff and how our solar system is so different. Could some of the planet stuff, like us not having those in-between planets, be related to only having one star?
That's weird too. That's a really good point. That's a great point, actually. Yeah. So, and there are radius gap explanations that involve collisions, right? So, or one planet knocks another one out, like a pool ball or something as well. But yeah, it is weird. We also seem to be one of the only solar systems that doesn't have a partner star, at least one that we can all agree or know about necessarily. That's a really interesting point. I'll have to think more about that. Yeah.
Just the chemical makeup of the core of the planet affected the size of its magnetosphere, therefore affecting how it's affected by solar winds. So
Yes. Yeah, I mean, I don't even have time to get into magnetospheres, but they're really, really poorly understood, unfortunately. Earth has an enormous magnetic field. Nobody else does. I mean, Jupiter does, but it's a very different situation. Why? People don't, it doesn't really totally make sense. The story that we tell about how the magnetosphere works, I think I might have talked about magnets a minute in this class earlier, but they tell this story of this swirling material inside of the magma underneath our feet, essentially, in the outer core and so forth. The problem is that Venus seems to have the exact same situation going on, right? Venus seems to have plenty of tectonic-y stuff going on. It seems to have plenty of magma. They think it's a very volcano-ridden place, and no magnetosphere whatsoever. So it's complicated. I think that we have to start thinking about how stars could get or how planets could get imprinted as well with magnetic fields as well, right? So you can imprint a paperclip with magnetism, right? So you can imagine that if a planet spent some time next to a star that had a really strong magnetic field, you might be able to imprint that on the core of the planet as well. Heck, you need a heck of an impact. Yeah, like a moon, like a world-ending impact. Yeah. All right, I should let you guys go. Think about it. We'll talk about the end of stars' lives next week, and we'll follow up with more questions about this too. See you guys.